So I'm going to start with a little context about myself and exactly what I will be talking about. So I live and work in Switzerland in a town called Lugano in the Italian canton, one of the two Italian-speaking cantons, sorry. And I'm part of a research and development group called Code Launch, where pretty much my title is junior group leader, but I do technical lead for the project that we do. We do collaboration with industry for innovation. We do a little collaboration with researchers of other faculties. We write the software to support the research. But also we are part of an institute called Software Institute in a university. So we are a group in a university, Università della Svizzera Italiana in this case. So we do also teaching. And that's the context where this talk actually comes from. So one of the masters that we have at the Software Institute is the Master in Software and Data Engineering. There are 4 pillars plus the thesis. There's a lot of stuff going on. In particular, there's a pillar about software engineering. And there, I teach a course called Engineering of Domain-Specific Languages. That's what I'll be talking about today. So what's a DSL? There are plenty of definitions, and I've seen these days popping up something in my Twitter feed that sometimes is also controversial, and I will mention a few controversial things about DSLs. So, but the DSL in general language targeted to describe the entities of a specific domain. And think about the domain as an area of knowledge. Can be any area of knowledge in engineering, in science, in whatever, or solving a problem related to that domain. And TLR, for example, is a DSL used to describe and construct parser generators. This is a sentence where you can use the term DSL. So I'm going to stay very, very general. So when I wanted to design this course, I had some topics in mind. I have many, actually. But let's say what I really want to talk about are external DSL first. So an external DSL is built and developed ground up. It may have its own ad hoc syntax and semantics. You can be very creative with that. It have their own lexers, parsers, and analyzers, everything like that. So imagine it like as complex as a programming language that is general purpose, but for a specific domain. Now, if you want to insert and teach something like that, the best would be, and only external DSLs, to focus on language workbenches, like IDEs that allow you to build these kind of languages. And in my mind, the best two that I know are the Rascal MPL, developed in research, and the JetBrains MPS. So these are really cool. In particular, if you have a look about what MPS can do and the case studies, there are DSLs, for example, to implement the Dutch tax legislation and process changes related to that, or something like a data analysis language to make biomedical scientists do the data analysis. And that's an example. So the problem is that if you really want to do a small course on DSL and external DSL, obviously you do only, and you want to use the language workbenches, you end up having to do just that. Because these are complex, they are not trivial syntax and semantics. MPS has even visual DSLs. So you can have visual components to your languages that are super cool, but they are non-trivial to construct. So in a small course, I didn't want to focus on that. But also for another reason, that most of the, so many important DSLs, especially for software engineers, they are not external, especially the ones that you can think about for testing. If you use any DSL in Scala, you know, right? So I want to talk also about, so I will need some space to talk about also internal DSLs that are built on top of existing programming language. They share the syntax, and obviously the semantics with the general purpose programming language. And now the problem is, which host programming language would you choose? So having worked with many languages, I wanted like a typical synergy that you would have in this context. So for example, you can decide to pick a language where you have a very cool internal DSL for parser construction that could support the teaching of an external DSL. And now the candidates are many. So I'm not going to say the Scala is probably the best. Probably yes, in my personal opinion, but people may not agree. So, but it's definitely a candidate. And I'm arguing you in this particular talk that there are other stuff, in particular, other synergies that particularly motivate this choice. So the key idea here is to use an internal DSL to support the external DSL construction. So, but I had the problem that my students didn't know Scala beforehand. So I had to find a way to introduce it without too much hassle, let's say. And can you do it with some kind of connection to DSL? And the answer is yes. I'm going to argue that you can do domain modeling in a very abstract way and then introduce the basics of Scala through functional domain modeling. Maybe it's obvious, but I'm going to show you that there are things in other areas of software engineering that particularly support this. Finally, the choice of Scala also allows to compensate some of the benefits that you will get with language workbenches regarding IDE support. And this is something that it's particularly effective, I think, for teaching, and some very unique advanced topics like generative DSLs. And that's pretty much the contents of my course and the contents of this talk. So I'm going to mention just a little how my students are, supposed to verify what they learn through assignments. I will mention the ones related to external, internal DSLs, and the last one, which is actually optional, so they can choose either one of the IDE support or on generative DSLs. OK, that said, let's start. Oh, sorry. So the goals are to learn the basic and the advanced concept of DSLs, and in parallel, learn Scala and on Scala support these topics. So let's start from the domain modeling part. So the idea, again, I want to introduce Scala, and I want to introduce the basics of DSLs. So my reference book for this part is this book from Martin Fowler. If you're interested about DSL, this should be your target book. It's general, it doesn't use Scala, but it introduces a lot of background, which is fundamental. In particular, a toy domain, which is the Gotti security domain. Martin Fowler used it in like many other books, and it's very effective, I think. So imagine a bedroom and a company that would sell devices like this. You would have a system that would allow you to have secret compartments, for example, in a plug that normally are locked. And they can be unlocked by doing a certain set of actions, like closing the door and then opening the second drawer on the left bedside table and then turning on a lamp. And these two in any possible order. And then what would happen is the door would be locked and the secret compartment would be open. Now, this domain, so imagine that the company actually developed something like that, and this is an example of a system called miscreants controller. Well, this is pretty much a typical software engineering domain. It's a state machine, where the states actually can control the environment, so they can lock the doors, they can unlock the compartments, and the events come from the environment. So there's some actions. For example, there's a sensor there that would activate certain transition and change the state of this system. So this is like the toy domain. And normally you would describe it in natural language, and here is a description. I don't want to spend a lot of time on that because this should be a domain that you're familiar with. They're a state machine with some kind of flavor. But the point is that can you use something different to represent it that you can leverage somehow? And the answer is yes. So what I use here is a notation. Imagine like a sort of class diagram, but without software concerns. And the author of the book probably would kill me for what I just said, but I'm just simplifying here, OK? So it's a visual notation that has a very simple semantic based on sets and relations. And this is what you get. So this is like a description of the same domain based just on sets and relation and classification. So what seems a generalization there, it's actually, again, classification, and the rest is structure via relations. So you don't have attributes, you don't have anything like that. So a notation like this serves to me to introduce actually the basics of Scala. And in particular, what I tend to construct is what Fowler calls the semantic model. So a DSL typically, when it gets parsed if it's external or if it's executed if it's internal, populates some pieces of some software entities. And these software entities are typically called the semantic model. So I want to construct then the semantic model out of the domain model with the notation that I showed to you. How can I do that? Well, this is pretty much a one-to-one mapping with a typical functional domain modeling that you have in Scala. So whenever you have these boxes and their own relations, what you have pretty much is product types with case classes. And on the other hand, when you ever have classification with the generalization there, you introduce seal traits, so some types. That's it. So that's how I introduce the student to Scala without any other complexity. I also put a required there to just show a bunch of constraints that you can have. But that's pretty much it. Basically, maybe some basics of collections and stuff like that. But no more than that. So really, really the basics. After I've done that, the domain modeling part is kind of finished. And I can start the external DSL part. So the objective here is to construct, so to be both a creator, an engineer of a DSL, and a user of a DSL. And in the meanwhile, introduce more advanced Scala features like variance function, and I'll tell you how. So the first choice is which combinator library or which parsing library do you choose? Well, there are Scala parser combinators, a perfect alternative. There is parboiled. When I did this course in Scala 2 until 2 years ago, that was my choice because we used it in practice, in production for a couple of engineering projects. But then it wasn't supported for Scala 3 until some months ago, so I couldn't use it, and I moved to Scala parser combinators, but pretty much you could have considered also something like fastparse. Here, they're both very valid DSLs. They all serve the purpose that I want. The choice is purely personal in this moment, and apart from the support for Scala 3. So this is the version of a DSL that I present to the students, and I try to teach them how to construct a parser out of it. And I'm going to use, again, this is Scala parser combinators. As you can see, I'm using a mix of operators and not. But the point is that when I do something like that, I teach them very important aspects. In this case, is the fact that this is, you can see this as a language. I don't tell them what is the tilde, apart from a simple operator in Scala on this particular DSL, actually. So I don't tell them that these are methods. I don't tell them anything like that. I just teach the language itself as a user. And then the point is that I also tell them, look, there are things here that are strange. Like the typical notation you would have for these declarations are not very common because these are values, but with the uppercase letter. And here, since it's representing a rule, this is something that it's quite typical. For example, the style of parboiled is exactly something like that. And the keywords there, I'm using the backtick notations because maybe they overlap with the Scala identifiers, or because they have some strange symbol that I want, and then something like that, okay? So I teach it as an independent language, even if this is Scala, okay? So whenever I introduce then a semantic action, so the idea to, while you parse, to reconstruct the semantic model, I can introduce a little more interesting Scala features. So this is the combinator syntax. And there are plenty of things here that are kind of new. For example, variance, like in this case, to tell them exactly what is this generic type parser. I can teach about functions. I can teach about pattern matching. I can teach about partial functions and a couple of other things, okay, that I'm not detailing a lot. But the point is that here I'm building on top even higher order function in this moment to manipulate collections and stuff like that. So I'm kind of building on top. I actually try to do it a little in the opposite way. So I first show this syntax that looks, again, unfamiliar, and then I explain it what it is. So in theory, you could also use this syntax without knowing exactly what's going on if you think about this as a DSL. But at this moment, I'm trying to reveal a little set of secrets. So I'm not going to dig too much about the external DSL assignments, but I try here to focus on languages that they know. For example, I typically focus on exercises to construct like subdomains of plant UML, so fragments of plant UML, of Mermaid.js, so that they can at least understand what is the purpose, okay, for modeling in software engineering in general. So after that, I can move to internal DSLs. And now I can really open the curtain and reveal a bunch of things. So the point here is that DSLs, when they're internal in this case, they are like any other library with a couple of particular important properties, like fluency or domain-specific syntax. And well, I teach which Scala features allow to effectively bend the syntax and break conventions. For example, I start with the toy language, like a mini version of Squants. Squants, if you don't know it, it's an amazing type-level library to do quantities, unit of measure, dimensional relationships. So this is my micro version. So lengths and areas manipulation. I can create a length of 1 meter or 1 kilometer, add it up, scale it, and multiply to obtain areas and stuff like that. So now I can tell what are operators in Scala. They're simply methods with one parameter and a symbolic name. And they are called in an infix form. So this is already, students already are surprised about this particular thing, but I found it extremely cool. When I learned Scala, this was one of my first wow moments. And even methods that are not symbolic, you can call it an infix form, and you can use it to do a lot of creative stuff. Now, the other day on my Twitter, like there was something, and I leave it as a quiz, and we talk about it. Can you add a Python-style power operator like star star in Scala? Who thinks yes? Who thinks no? Okay. So then the point is that I can introduce stuff like extension methods that in this case are the use cases to mimic postfix unit of measures, like this 1.m, 1.kilometer, and so on and so forth. Here it's a simplified version. I'm using only double as an extension. And as a side feature, I lead the modularity with the companion objects. So this is Scala 3 syntax. With extension methods, adding possible methods in a context, like in this case of an object of type double. Okay. So after this, one of the most controversial properties of DSLs, fluency. So a Fluent API, which is typically in other language what you would describe as a DSL, it's an API that reads like natural language. And what I teach here, how to construct in Scala Fluent builders. Here I have a builder that constructs a rectangle, reusing the stuff that I had before, with base of something and height of something else, right? And I also tell them, look, this is very verbose, very annoying to construct. If you use symbolic methods, you can even simplify because of precedence. And then maybe on the side, another quiz, you may think if that's fluency in another sense, if that is valid Scala and if you can do it. Think about it. The second is how to express a date in Japanese. And that's perfect Japanese, as far as I know. But it's also valid Scala. That's the question. So in the last lecture, I complicate the Gotti security language with guards, effects, counters. So I make it a little more complicated. And this allows me to introduce stuff like call by name or by name parameters that allow, for example, to reuse pieces of code. And here, the guard here, that expression on the guard with after the equal is not evaluated at where it's defined. It actually can be evaluated in the body of the method, but the point is that you don't want to do it. You want to do it later, so you typically box it in a function without parameters in this case. And there I have a method that actually constructs the domain model entity that holds the expression that I defined in a call by name parameter. So finally, again, the last part, I try to split and add something on top of this language, which are assertions. Whenever you have an assertion, for example, you want, or a set of assertions, so you can say that a set of events brings the state machine in some final state, then what you can use, for example, are givens and contextual abstractions in order to, for example, simplify a little the language. So you kind of define your model, your state machine, then you import it, you define the state machine as a given, and then you can call the assertions that refer to that state machine. So the code is actually not that complicated, but I don't want to go too much into details because I have more cool stuff to show. So I just want to show you shortly what are the kind of internal DSLs that they can develop in the assignments. Here you can see, for example, an assertion language that kind of resembles maybe a mix of Scala test or the akka testing libraries and extensions for that. In this case, you have a stupid toy language for URLs that actually is just an exercise on operator usage and precedences. But then the rest is something very reasonable. Like in this case, I'm asserting that eventually a get will respond with the status code. And this is what I mean by fluency. I read the code and it reads like natural language, right? And you can go complicated. Actually, these are the best students in that case. They did an optional part where you can have, for example, assertions on headers, matching regular expression, or containing and doing combinations. And in this case, I tell them to do it like that, but then they have to tell me why it's wrong or why it's problematic to have the end like this. And this is like a problem in DSL design in Scala, that this is the use of and here to combine in condition is problematic. OK. So after internal DSLs, there's the complicated part and cool part that I really like to teach because it's, again, something that not many programming languages have together with the rest. So a generative DSL actually allows me to introduce metaprogramming. I used to do it in Scala 2. It was painful. In Scala 3, it's way easier for me. And I do a bunch of things. So the first one, well, let me tell you a little motivation. So this language that I showed you before is very verbose. So because it's fluent, it has a lot of things that are a little repetitive. So for example, the toggles counter there, I need to specify the name, but I would like actually not to do that. There's already the name of the variable. Or I can, for example, I would like also to have custom errors. So this DSL, when it's internal, would fail if you declare two initial states. I want that to have like an error at the IDE. Can you make it? Well, the answer is yes. If you construct a generative DSL where part of the code is generated at compile time, so during compilation, you can do something like that. And again, it's a toy language, but it's kind of cool. So I'm leveraging Scala 3 metaprogramming maximum and reflection. But before digging into that, I'm going to show you just a little demo of what I mean. So that's my language. It's a little different. Here I'm starting with this sort of keyword, if you want to see like that from a DSL point of view, state machine. After that, I enter the DSL. For example, code in my language, they need to be 4 letters. If I put 3 letters, I get an error. OK? If I do 5 letters, I get an error. OK? So they really need to be 4. Other thing, if I have 2 initial states, by mistake, a compiler error. OK? Actually, it's a custom error, not really the compiler. These are my macros. Or same thing if I don't put any initial state, which is kind of bad, right? OK, so how do you do that? So you do that by leveraging macros in Scala 3. So all goes around this type, which is expression of T, which represents like a typed abstract syntax tree for an expression of type T. And everything goes around splicing and quotation that allow you to move between these two worlds, the world of ASTs and the world of normal types, let's say, in your language. With splicing, you take something of like an AST, and you can actually embed it, and so generate code. And on the other hand, if you have instead a normal type and you quote it, you get the AST. So now I'm simplifying. There are plenty of complicated rules here that need to be there in order to generate code and combine splicing and quotation. But the idea is that this language, from the syntax point of view, has no semantics. So on the right, there's the DSL. On the left here, you can see actually the methods that define the syntax. And that's it. OK? So they are all unimplemented. It's the state machine method that actually rewrites this code and actually generates the semantics for my language. OK? So I'm doing it through macros. So this is the entry point. I want to maybe just say, it's like almost by heart that all macros have this form. The second method there, which is the implementation, takes an expression of type transition, which is the block of my DSL, and rewrites it into the domain model class, which is a state machine. And that's it. Over there, it's just rewriting and checking. What do you get? Well, this is an example, an interesting one. So this rewrites a command that val locpanel equals command of code pnlk into a call, actually, to a command of locpanel with the code. So I'm calling here the apply methods of my case classes, and I'm regenerating, actually, the code as I like. So a bunch of things. Here I'm actually using reflection, so because there are value definitions there. So not the type AST as I told you before, but I start with the val definition. I have the command name, which is actually the name of that value, and the right-hand side of the val definition, which is this command def. And what I do, I check that it actually matches command of some string. And that's quotation used in pattern matching. So like I'm using pattern matching on code. I'm checking that the value, so that is pretty much a literal, and it has size 4. And in that case, I extract the string that represents it. In the other case, I generate errors with this report.error. And finally, I rewrite the code again with a quotation. So I take the expression, and this second line is equivalent to the comment that I have above, and I can redefine actually the val definition with this valdef.copy. So somehow I regenerate the right-hand side in order to match the code that I want. And that's it. Now, other parts are more complicated, obviously, but this is like just an example to show you how this works. So I'm going to show you then the other part of generative DSL that I show to the students, which is, sorry, I think, yes, this is it. An assertion language, again. But in this case, my assertion language is a little weird because I have this should have assertion where the type of things that you can assert on depend on an arbitrary type like this box. So here I can, this box label as label, weight, and price, and I can assert only on price, weight, and label. And so this assertion language depends actually on the type that you have to check. So if I, for example, put a typo, I get an error, okay? Again, a compilation error. And if you see actually in this should, there are a bunch of methods here that are defined that I'm not going to go a lot into how this is constructed, but I think this is very interesting. I'm just going to mention how this is constructed in a few seconds. So I want an assertion language that works on arbitrary types. The DSL methods here depend on the subject type. So if the person has a field called first name, I want to be able to assert on the first name, and I want to do it statically. I want even possibly to have support from the IDE. Unfortunately, since these are infix methods, this doesn't work really well with methods apparently, but it's just a question of implementing the feature, I guess. And how you do it is you do it with the type provider. So if you have heard this from F# or maybe by looking into the internal specs too, this is exactly how it's implemented there. So it's a macro that provides specific type definition in function of a subject type. And this is how it works. So I have, on top the assertion, the should have is actually a macro. That should method is a macro that, depending on the type of person, also my subject type, generates a selectable with the refinement type. So imagine just a refinement type where you have 3 specific methods, 1 for each field of the case class, or in general, 1 for each attribute or method with no parameters and so on when you return type. And these methods have the same name of the field and the parameter of the same type of the return type, the type of that specific field. So, and that's the first step of rewriting. So first, the macro generates the type, and then another macro, which is actually on top of the assertion language, rewrites this into a particular assertion. Actually, it should be 30, not 39, I'm not 30, but anyway. And what you can do also is to generate a custom error message. So that's, I think, pretty cool. Now, this is only optional. This is only for the best students from the assignment. And I want to show you what, actually, I tried to use a little creativity here. I have complicated stuff, like, for example, basically negation of parameters, like this should not have. I can have inequalities, and that can get rewritten. Obviously, this, from a syntactic point of view, it's not easy. Or I have even higher order declaration of this form, like all in a list should not have size greater than 0, something like that. Or some or none in blah, blah, blah. So these are the kind of the assertions that you can create with this approach, combining Fluent Builder construction and generative programming. And this is similar, again, what you have on specs too. OK. So by the way, typically only 1 student per year, maybe 2 try this. Sorry, student pair, because the assignments are paired. But they usually get a 10 if they try this, because they are the best. OK, so to finish, I'm going to just mention IDE support. There is not a lot of specific magic, but there's something peculiar to Scala here. So the idea that in generative DSLs, I get errors in the IDE, and that's cool. But with external DSLs, I just had the script that analyzes a file and gives me error in the command line. That's bad. I want support in the IDE. How can I do that? Well, for research that we do at Code Launch, we learned a lot about the internals of Visual Studio Code. This is our favorite editor for Scala and for TypeScript. So we know it, but we also know the internals. And we know that it's highly extensible and customizable, right? And in particular, that you have programmatic language features. So if you know metals, all the things that are in metals in the language server, there is like a sort of simplified version with simple APIs that you can have and you can use in extension of VS Code without implementing your language server, okay? Can you leverage this? Well, the answer is yes. But the problem is that obviously Visual Studio Code is written in TypeScript, and the APIs are in TypeScript, the extension is in TypeScript, everything is in TypeScript. So the idea is that, well, I cannot definitely introduce another language, worse TypeScript, which is non-trivial, and the APIs. So how can I do that? Well, fortunately, the synergy here is called Scala.js. I think you know it. So it transpiles to JavaScript code. And in that case, it can run in any JavaScript environment, including Node.js, so including the environment where actually Visual Studio Code runs. Visual Studio Code, it's an Electron application, so in the end, it's a Node environment. And the cool thing is that, well, on one hand, most Scala libraries cross-compile for Scala.js, and on the other hand, all the types that you have in TypeScript through scalably typed can be converted into Scala types. So pretty much what I have to show the student is just some Scala code that actually calls the TypeScript APIs. And the complexity is really little, okay? It's not that much. There's only certain things that they need to be aware. For example, here you see a seal trait that represents a token with positional. This is the typical way you would do it in the Scala combinators. And there I have a lazy val that generates a V range. This is like a Visual Studio Code type. And I already have the constructor from scalably typed. Same thing, for example, for document symbols that allows me to generate breadcrumbs. It's just a call to an apply method that is generated automatically. And in the end, it's a call to TypeScript APIs. That's it. And even generating, registering the document symbol provider, it's trivial. The only ugly thing that you can see here, the thing that I don't like from Scala.js maybe, is the fact that in order to generate like an object literal, you have this syntax js.dynamic.literal, and then you need an existence of. Maybe there's a better way, but this is what I found in the documentation, I must be honest. I hope there would be a better way, and maybe there will be. Other things are like 2JS arrays, so these little conversions. But it's extremely cool, because in the end, this is what you can do. I'm going to show you in the end, just the result. What I normally ask the students to do is to, they start with some existing language features. For example, the symbols. So here you see the breadcrumbs over there. And now you have the breadcrumbs over here. These are the document symbols in Visual Studio Code. But things that they are definitely able to implement, for example, a rename refactorings like this. Then normally they are not there. Like waiting for light, and then all the instances are actually renamed. Okay. Other things, for example, definition providers. So you command click and you go where the thing has been defined, and even code lenses. In this case, I have assertions. I can call run, and actually it's not showing because it's in the output here. My got the security assertion output. This is a success. And if I run the last, I have a failure. So in this way, I've completed the, let's say, the story. And now I have IDE support even for my external DSL. And there are plenty of language features that can be very complicated. The students were able even to do recommendations, so like suggestions in the typical context. For example, that here you need a state, and you would get the list of states automatically in that particular context. So, I'm perfectly on time. I'm finishing. So that was the IDE support. Closing up. I hope I convinced you that even if your student has never seen Scala and you want to teach it with a different point of view, you can actually put a lot of, and teach most of the parts of Scala actually via teaching DSLs. And there are synergies in the language. Most of Scala can be presented and explained. You can reference to existing DSLs and existing library, maybe with some simplification. Most of the times I have to do that. But there are obviously a lot of missing pieces. So in Scala, functional, or let's say escalator style or type level DSLs are very popular, but I don't have the time with this content to explain them. So if the course was probably 6 credits, I could do that. But this is obviously not the only way to think about DSLs, okay? And other things like Kotlin style type-safe builders that you can do, for example, now in Scala 3, or even more advanced stuff like embedded DSLs or compilers, like the lightweight modular staging that was done on Scala 2. This is amazing work. If you don't know it, have a look. And I normally mention it like really in the last lecture of things that you can do. There are a couple of examples of things that are extremely amazing. So this is all. Thank you very much. I'm ready to answer your questions if you have them. And the 2 quizzes, maybe if you want to discuss, the answer are no. The star has a lot of problems if you do that. And the second case, the Japanese date, yes, this is valid Scala. Thank you very much.